going? Okay, so this is where we left off last time. I do not remember if we actually completed this part or not. I did forget to change out the damn figure though. Shit. Anyways, the carbanions are going to be the opposite in terms of stability for your carbocations, okay? And it's for the same reasons as the carbocations. So remember that when you're talking about a carbocation, you have an empty orbital, and that empty orbital is pulling electron density into it, right? When you have a carbanion, what do you have? What would a carbanion look like? It has an orbital that's full, right? That has a lone pair in it, okay? That orbital is going to have a negative charge, isn't it? So anything that would surround that with negative charges is going to do what? It's going to repel. It's going to be less stable, right? Okay. And so the carbanions will be the exact opposite trend to your carbocations. Okay? So the carbocation is less stable when it's in the methyl, and as you substitute it, it becomes more stable. The carbanion will be the exact opposite. It's the opposite charge, it's the opposite situation, right? Literally the opposite in every way. Okay? And so the order of stability is opposite. The least stable would be the more substituted one, right? The more stable will be the less substituted ones. Is that making sense? Okay. Fantastic. Okay, so this is actually your basicity when we're talking about carbanions. Keep in mind, carbanions are going to be extremely basic. They far exceed the normal 14 to 0 pH scale. Did you guys know what the actual pH scale ends up at? It's not actually 14 to 0, in case you guys are ever curious. The pH scale is based on the acidic forms of water and the basic form of water. So OH minus is 14. H3O plus, hydronium, is the quote-unquote 0, but it was never 0. It was actually closer to -1. I know, everything that we've taught you is a lie. What is that called now? Red pilled or? No, that's for Democrat Republican now, isn't it? Damn. They screwed up all the analogies. Okay. I have given you some sort of form of pill that has exposed the lie. All right. We've exited the matrix, as it were. Okay, so again, this is going to be basic. This is an example of the carbanion actually having that negative charge, stripping an H plus off of what we would normally consider a base, right? See that? That's the ammonia. We would normally consider that a weak base. So the ammonia here is acting as an acid, isn't it? It's donating an H plus. The carbanion is our base. This gives us the protonated carbon and would then give us the negatively charged amine. Okay? Or the amine anion. Does anybody have any questions about that? We're acting as a base. Ooh. Okay. So, again, the carbanions, they are bases. They are also nucleophiles, right? Keep those things a little separate in your head. Yes, most things that are bases are also nucleophiles and vice versa. That is true. But the strength of its nucleophility, how good of a nucleophile it is, how strong it is, versus its basicity, how strong of a base it is, those are actually different, okay? There are some things that can diverge. These are carbenes. So this is actually going to have kind of a weird hybrid situation, okay? So in a carbene, you actually have a carbon with a lone pair, okay? This is very distinct and different than having a carbon that is a free radical. Okay? So, you'll have an sp2 hybridized orbital that has a lone pair in it. You'll also then have an empty p orbital right here. So because it has a lone pair of electrons in this sp2 orbital here, this can react as a nucleophile. It also happens to have an empty p orbital, which means it can act as an electrophile. It can both donate a pair of electrons and accept a pair of electrons, right? At the same time. Isn't that fun? Okay? So this is a super reactive species that can react in a tremendous number of different ways, okay? It's extremely high energy, very unstable, by the way. Carbines are neutral because it has the same number of protons and electrons, right? No charge. So this is actually carbene as a reaction intermediate. You're never going to see them as something we can put into a reaction. They're too unstable, they're too reactive. As you may have noticed, it can act as both, right? So if you put carbenes with each other, what would happen? Well, one would donate its lone pair to the other, right? So there you go. They can do both, right? So one would act as electrophile, one would act as nucleophile. You could have an electrophile and nucleophile pair that are both carbenes. Same damn thing. Congratulations. Okay. Nice symmetry, right? Yes, yin-yang sort of stuff, right? Okay. This is actually an example of a carbene being formed. So what you have here is a strong base reacting with this aldehyde here. It's going to pull a hydrogen off. That would leave a negative charge on the carbon at first, meaning that would be a carbanion, right? But notice it has a double bond next to it. When you see delocalized electrons next to each other, like for example a carbanion that has that lone pair up in the p orbital, right? That's going to overlap with the double bond. And what that means is that the electron density can actually flow over to oxygen. Which is more electronegative, oxygen or carbon? Oxygen. By the way, if you wonder why I do this thought process, I'm trying to expose the inner thought process of a chemist for your brain to follow along with. Okay? I'm not actually doing it to hear myself or have you hear me. Like, the important part is not my words, it is you following that thought process with your brain. So you can start forming that thought process yourself. Okay? Is that making some sense? Like, there's nothing in organic chemistry you can't just reason out from base concepts very quickly. Okay? Okay, so the electron density is actually going to flow over and mostly go over to the oxygen, right? The oxygen is going to hold on to most of that electron density. And so what ends up happening is you actually end up with a mostly carbene on this carbon here. Okay? Does that make sense so far? Anybody have any questions? Could everybody follow along with that logic chain okay? Yeah? Kind of? Okay. Yeah. Actually, please do try, because it's actually the thing that will give you the most value out of your college career, is to form that ability. Okay? The individual, what a carbocation is versus carbene, is not actually as important as that. Right? That's the most valuable thing I can give you. Anyways, these are right here are the stabilities. Notice that the carbenes don't really have an order of stability here. Typically, the only way to form a carbene is to have some form of resonance structure or some very extreme conditions. And so resonance structures will stabilize them, but it's not a tertiary versus a primary is going to be more stable, okay? Because they're both a nucleophile and an electrophile. They don't have a charge that they can either share or would be destabilized by negative charges. Okay? All right, that's that chapter. We'll go ahead and move on to the next now.